All right, welcome to this explainer on the cosmic engine cycle, unpacking X-ray bursts. Today, we're diving straight into how some of the most powerful, earth-shattering explosions in the universe happen on objects no bigger than a city. We're talking about thermonuclear X-ray bursts. These are phenomena that take the physics we understand here on Earth and just stretch them to their absolute mind-bending limits. Let's get right into how they happen and what they can tell us about the very fabric of the cosmos. So take a look at the staggering number. That is 10 to the 40th power ergs. It's an absolutely massive amount of energy. And it's exactly what's released in just seconds during a typical thermonuclear X-ray burst. To put that into perspective for a second, that is more energy than our entire sun will output over a whole week, just unleashed in a blinding flash lasting tens of seconds. And the craziest part? This happens over and over again on the surface of a neutron star, which is basically the ultra-dense remnant of a dead star packed into a tiny sphere maybe 10 or 12 kilometers across.
Let's move on to our first main topic: cosmic vampires, binary systems.
So where do these incredible explosions actually come from? Well, they happen in setups known as quiescent low-mass X-ray binaries, and it's basically a parasitic relationship. On one side, you've got a living, relatively normal companion star, usually a bit less massive than our sun. On the other side, you have this dead neutron star. Because they orbit each other so closely, the living star actually swells past its gravitational bounds, a limit physicists call the Roche lobe. When that happens, the neutron star, with its immense gravitational pull, just starts relentlessly stripping hydrogen and helium right off the surface of its living companion. And that relentless theft brings us to the next phase: pressure cooker, the accretion.
As that stolen matter crosses over, it doesn't just fall straight down, because the whole system is spinning. The material keeps its angular momentum and spirals around the neutron star, forming this flat, glowing halo we call an accretion disk. Over time, friction within this disk causes the material to lose energy, so it slowly spirals inward and violently piles onto the star's surface. Now remember, the surface gravity of a neutron star is absolutely intense. So this freshly accreted material gets instantly compressed into a supercritical state by what is essentially a gravitational vice grip.
Eventually, all that compressed fuel has to go somewhere, which leads us to ignition, thermonuclear runaway. Now, during pauses or slight slowdowns in this accretion process, that extreme gravity acts like a giant cosmic sorting machine. The heavier helium atoms get gravitationally pulled downward through the lighter hydrogen. They're literally sinking on a timescale of just tens of seconds, kind of like heavy rocks dropping in water. This leaves a nearly pure hydrogen atmosphere sitting right on top, perfectly setting the stage. Beneath that surface, though, the temperatures and pressures are climbing so incredibly high that the helium and hydrogen are forcefully fused together, triggering unstable nuclear burning. Now, you might be wondering, why does it explode? Why doesn't it just burn steadily like our sun does? Well, it all comes down to this concept: thin shell instability. Basically, it's a condition where a radially thin layer of accreted fuel can't expand to cool down, causing a runaway temperature increase and explosive nuclear burning. Think about it. This fuel layer is maybe a few meters thick, sitting on a star that's 10 kilometers in radius. Normally, when nuclear burning starts and heats up a gas, the gas expands, the pressure drops, and it cools down. It's a natural safety valve. But here, the layer is so impossibly thin and pinned down by such massive gravity, it simply can't expand enough to release the heat. So the temperature spikes. That increases the nuclear reaction rate, which generates even more heat. It's a total runaway train. And this runaway reaction doesn't just sit in one spot. As this quote captures perfectly, the burning is unstable and engulfs the entire surface of the neutron star in less than a second. Just try to picture that for a moment. A massive wave of nuclear fire sweeping across an entire city-sized sphere in the blink of an eye. The resulting flash of X-rays is so intensely bright that it completely outshines the whole accretion flow. For a brief window, it becomes the brightest thing in its local cosmic neighborhood. Of course, not all bursts are identical. Let's break things down in burst types and superbursts. These explosions actually come in a few distinct flavors, depending on the fuel and the exact mechanism. First, we have ordinary Type 1 bursts. These are the ones we've mostly been talking about, driven by hydrogen and helium fusion, and they last somewhere between 10 and 100 seconds. But then we have Type 2 bursts. Now, these are a completely different beast because they aren't nuclear explosions at all. They're actually powered by spasmodic, sudden drops of matter falling directly from the accretion disk onto the star, releasing a massive amount of gravitational energy.
And finally, we have the incredibly rare superbursts. Basically, after thousands of normal Type 1 bursts, carbon ashes pile up deep, deep down in the star's ocean. When that carbon finally ignites, it triggers an explosion that is up to 1,000 times more energetic than a normal burst, and it can literally last for an entire day.
To really wrap our heads around these events, we have to look at the hard data. NASA's NICER observatory, up on the International Space Station, monitored a specific system called 4U 1820-30 and caught 15 bursts. What's absolutely fascinating here is a phenomenon called photospheric radius expansion, or PRE. The radiation from the explosion is so intense that its outward push literally overcomes the star's immense gravity. It blows the star's outer atmosphere tens or even hundreds of kilometers out into space. In one wild instance, NICER recorded a super expansion where the atmosphere was blasted out to a staggering radius of 902 kilometers.
But wait, it gets better. During this observation, NICER didn't just see the atmosphere expand. It picked up a mind-blowing burst oscillation right at 716 Hz. You see, burst oscillations happen when the nuclear burning isn't perfectly uniform, which creates a ridiculously bright hotspot on the star's surface. As the star spins, that hotspot sweeps past our telescopes over and over, kind of like a cosmic lighthouse beam. If this 716 Hz signal is fully confirmed, it means this neutron star is spinning 716 times every single second. No joke. That would make it the fastest spinning neutron star ever found in an X-ray binary.
So why does all this matter? That brings us to our final section, laboratories of extreme physics. Why spend so much time analyzing flashes of light from thousands of light years away? Well, because these bursts are literally our best window into the unknown. The escape velocity of a neutron star is around 200,000 kilometers per second. That's so high that almost all the ashes from these bursts stay permanently trapped within the star's gravity well, eventually forming a new crust. By analyzing the light curves and the cooling tails of these bursts, scientists can effectively peer deep inside the star. It lets us measure the star's mass and radius with incredible precision. And honestly, that's really the only way we can figure out the equation of state for ultra-dense matter. Matter's so tightly packed, we could never even dream of recreating it in a lab here on Earth.
Furthermore, it's not just about density, It's about chemistry. As this shows, X-ray bursts help map the origins of heavy elements through the rapid proton capture process, or RP process. During that explosive flash, lighter elements are rapidly fused into much heavier nuclei, potentially creating elements all the way up to cadmium or even beyond. So by studying these bursts, we are quite literally watching the cosmic origins of heavy elements being forged in real time. It helps us piece together exactly how the universe chemically evolved to become what we see today. So, as we wrap up this explainer and continue monitoring the skies with tools like NICER, we really have to ask ourselves, if a city-sized dead star can generate the most powerful explosions in the galaxy, what other fundamental laws of extreme physics are waiting to be uncovered in their nuclear ashes? Every single burst we observe brings us one step closer to understanding the absolute limits of physics, gravity, and matter itself. Keep your eyes on the stars because they clearly still have so much left to teach us.